Okay, let's see, number 11 says solve a given rational equation. How do you solve a given rational equation? Well, first you got to know what a rational equation looks like. It's going to be a polynomial divided by a polynomial plus a polynomial divided by a polynomial maybe equals another polynomial divided by another. It involves polynomials divided by polynomials. Now, if you have polynomials divided by polynomials, you're going to have denominators. You factor all those polynomials and find a common denominator, and it's most convenient to find the least common denominator, and hopefully understand how to do that. And then you multiply both sides of the equation by that, hopefully the least common denominator, but by any common denominator. If you can't find the least common denominator, just be sure you use a common denominator. All your denominators will get cleared when you do that. Then you solve the resulting equation. You do have to be a little bit careful that none of your solutions are zeros of your denominator. Because, of course, you can't multiply both sides of an equation by 0. And it's related in a way that I'm not going to detail right now. Solve a given radical equation. That's like you got a square root of x plus 5 plus 7 equals the square root of x minus 9. Whatever. It involves square roots. Okay? First of all, you rearrange it into whatever form you need. You want a square root equal to something else. Then you can square both sides, and that square root goes away. It becomes something that doesn't have a square root. However, what you squared over on this side might still have square roots in it, and you've got to be really careful that you square both sides using the distributive law. If there's more than one term, you want to use the distributive law. Otherwise, there are traps that you can fall into. You might think that if you square a plus b, you get a squared plus b squared. You don't. You get a squared plus 2ab plus b squared, and you get that if you use the distributive law instead of using superstition. Okay, because, you know, that what I just talked about there, if you square a plus b, you get a squared plus b squared. That's superstition. It doesn't hold up. You square both sides. You write a plus b times a plus b, and you don't get a squared plus b squared. You get a squared plus 2ab plus b squared. So use the distributive law with whatever the expressions happen to be. Okay? Well, anyhow, if you do that, you might still have square roots. Okay? If you do, you repeat. That is, you rearrange to where the square root is on one side and everything else is on the other side, and you square it and you get rid of that square root. Now, that still might give you a square root, so you repeat until you don't have any more square roots. Okay. Number 13. Solve equations giving for inequalities involving absolute values. The thing you have to understand is that any such equation is almost certainly going to split into two equations or two inequalities. If it's an equation with absolute values, it'll split into two equations. If it's an inequality with absolute values, it'll probably split into two inequalities. So this is a step people just aren't doing. They just remove the absolute value signs and solve it. You know, I'm not going to be real generous with points if you do that. And this is something people did quite well in class, so, you know, didn't necessarily follow up very well with it on the test. So make sure you got it. Number 14, give the geometric number line description of a given absolute value equation or inequality. Not giving you the complete picture of what you do. You have to start with the fact that the absolute value of a minus b is the distance between a and b, period. If you start with that and give it a little practice, you'll understand how to do number 14. Number 15, given the completely factored form of a polynomial function, sketch its graph. I'm not sure I gave you a complete result for number 15 because I was kind of looking at number 16 as well. But the point is that for a polynomial function, your polynomial function reduces to product of linear and irreducible quadratic factors. Linear factors give you the zeros. Irreducible quadratic can't be zero, so the irreducible quadratics cannot be zero. I probably should also zeros partition the number line, and the magnitude approaches infinity. You're not going to be able to read this. Maybe you will. At each end. Okay? I'll kind of put that down as a reminder to make sure I mention that, because I should have mentioned that with number 15. Now this covers number 15 and number 16. What do I mean by magnitude approaches infinity at each end? I mean, if you go out past your last zero, the thing is either going to be positive or negative. If it's positive, it's going to pretty rapidly take off for the sky. And if it's negative, it's pretty much going to descend rapidly, approaching either positive infinity or negative infinity as x approaches infinity. Number 17, intermediate value theorem. And the statement I make here is, if it's a polynomial, so I say, and if it's a polynomial, probably should have started with if it's a polynomial. But, okay, if it's a polynomial and it's less than 0 at one point and greater than 0 at another point, then it's 0 somewhere in between. Why is this? It's because a polynomial always forms a smooth graph, either coming down from infinity or coming up from infinity, goes through 0. If it does go through 0, a quadratic polynomial might be completely above or below the axis, and any even power might be. But it's typically going to come up or come down, go through 0 a couple times, a few times, and go back either up or down. From all the way over there to all the way over there, it's a smooth function. And it's continuous. It doesn't have any breaks. That means if it's lower than 0 here and higher than 0 over here, it's going to have to go through 0 to get from below 0 to above 0. So there's going to be a 0 in between, any point where it's below 0, any point where it's above 0. There might be several zeros. You might do this thing, okay? But it's a fairly obvious statement, and it's not always true for any function. It's true for polynomials. And there are a number of other functions that it would be true for. It's not true for a rational function. By contrast, a rational function can have a vertical asymptote, and it can be come down from the vertical asymptote and approach the negative x-axis without going through it. And then on the other side, it can come away from an asymptote below the x-axis and then approach the vertical asymptote. So it's approaching the vertical asymptote on the positive side here, and it's positive all the way over here, and it's approaching the vertical axis from negative numbers over here. Well, it's positive over here, it's negative over here, but it never goes through 0. Okay. A rational function can do that, but a polynomial and many, many other functions cannot. Okay, 18. Talk about dividing one polynomial by another. And we do that by long division. I mentioned that synthetic division is okay, but I see no point at all in synthetic division, simply because, in a pre-calculus course, simply because unless you're dealing with a lot of polynomials and dealing theoretically, you're not going to need synthetic division. It's efficient. It's an efficient way of dividing a polynomial by a polynomial, but it's based on long division, and I stick with the base. If you ever need synthetic division, it's really, really easy. Okay? If you understand long division, then in 15 minutes you can understand synthetic division and use it as much as you like. So if you want to use it, okay, unless I ask you to specifically use long division. But I think it's not worth the time in this course. Other people can have other opinions, and that's fine, because other people have other goals. And they're all good goals. So I have no objection, but I don't do it. And it can appear in the assessment. You know, if the assessment says do something by synthetic division, you know what? So be it. I'm going to ignore it. And anybody who's looking at the assessment will know that I don't do synthetic division. Everybody omits things, and that's one thing I omit. Okay, number 19. And what does number 19 say? It says, given a rational function, construct its graph. So all I'm saying is, if you've got a rational function, that's like a polynomial divided by a polynomial, you factor it out. You get the numerator into linear and irreducible quadratic factors. You get the denominator into linear and irreducible quadratic factors. Now, if you know, that can be easier said than done. It's not easy at all. It's pretty much impossible if you have a big polynomial, but theoretically that's what you have. The zeros of that polynomial occur when the numerator is 0, and vertical asymptotes can occur when the denominator is 0. They don't necessarily occur because, I say here, unless you have the same zeros for numerator and denominator, in which case that means you have, say, a linear factor up here that matches a linear factor down here. They would divide out. I don't like the cancel word. Don't try to avoid using it because people do it so badly. But if you have a linear factor here and a matching linear factor here, you divide this one by this one, it gives you 1, and you don't have to write 1 as a factor. So unless they're the same zeros for numerator and denominator, maybe. Because, of course, you could have a linear factor up here and the square of that linear factor down here, and this linear factor would only divide out one of the two that you have in the square. So there are all kinds of things that can happen. I'm not going to go into all that detail, but you got to think about those things and follow procedures. But the bottom line is that zeros occur when the numerator is 0, when the numerator zeros aren't matched by denominator zeros, and vertical asymptotes occur when the denominator is 0, provided the denominator zeros are not matched by numerator zeros, but sometimes even if they are matched, you still have those things. So you can locate zeros and using a little common sense, asymptotes. So you partition the number line between zeros and asymptotes. The only place the function can change sign is at a 0 or a vertical asymptote. And you use that as a basis for graphing your rational function.